Hello physics students, so we're going to start looking at light as our next topic. So we've talked about the idea that if you have a charged particle, there's an electrical force field around it. So in this case we'd have one going outwards, and you could draw it and represent the field with those field lines going out, and you could draw more in there. But the idea here is if you actually can get an electric field produced by a charged particle and cause the particle to vibrate or oscillate, as the particle goes up and down, it will change the shape of the electric field around it, and you'll find it will follow a shape that's slightly different. So it will actually produce a field that's like this, and so the electric field will have this sort of shape where it goes as a wave. When it's actually vibrating up and down, you get a wave in electrical field going outwards, and so that will be electric field oscillating upwards and downwards in the vertical plane in this case here, if the oscillating charged particle is going up and down in the vertical plane. So the other thing to keep in mind though is that when you have an electrical current going through a wire, or electric charges moving through a wire, you'll find that the actual magnetism is generated around that. So an electric current generates a magnetic field. So the magnetic field is actually generated at 90 degrees to that electric field, and you can show that sort of electromagnetic wave that's produced by that motion then, something similar to this here. So an electromagnetic wave that's actually generated by that charged particle would represent an electric field going in the vertical plane here, up and down by the red section, and there'd be an oscillating magnetic field going at 90 degrees to that simultaneously, and that's why it's called an electromagnetic wave. And you can draw it a few different ways. This one here is sort of draw more of a 3D view, but the red's the electric field vectors going first of all downwards and then upwards there in that plane, and the other plane at 90 degrees is the magnetic one. So that's just some things to bear in mind. Now there's a whole electromagnetic spectrum depending on how fast you vibrate that charged particle. Okay, so if it's going relatively slowly at low frequencies, you'll get what's called radio waves there, and you get a change in the frequencies causes a change in the types of waves, and also how it's generated produces the different names of the waves. So microwaves have got a slightly higher frequency. Infrared, you've got things that are warm basically, and that sort of frequency of vibration of the particles in the nuclei will give you higher frequencies and higher frequency light or higher frequency electromagnetic radiation. And then you go into the visible section when it gets a bit hotter, and you can go from red through to violet, ultraviolet, X-rays, and then to gamma rays, which are the high energy ones. So the frequency here is getting higher as you go off to the right, and there are those different types of EM waves all travelling at the speed of light, and you could call all of them light, but only one section is visible to us, obviously that visible region there. It's a very narrow portion of the spectrum, so just bear that in mind. So let's look at refraction specifically here at the moment, because that's our focus. When water waves enter a narrower region here, and they enter this region here, might be shallow water, the result is to do this.
One side is slowed down before the other, forcing the wave front.
Now what you can see happening here is the wavefront that's coming down there is a certain wavelength apart, and as it enters this new medium, just at this boundary here, it changes speed, and the first proportion of the wavefront to hit that will slow down first and obviously lag behind the rest of the wavefront that comes down. Then the next bit comes down, and that sort of comes and hits here and then sort of follows, and so on. So the change in direction of that due to the change in speed causes it to bend down like that. Okay, but it's because the wavefront hits the actual edge at different times, and it slows down to different proportionals. So you just see that again in motion there.
To change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction.
So that bending of light is called refraction, and that's what we're sort of studying at the moment there. They're focusing on the refraction of light here. So we'll just close that off there. So if we look at some examples of this here, there's a couple of things to bear in mind. The incident ray here is actually incoming ray, and it hits the boundary surface here, and it forms what's called the incident angle, or the angle of incidence, and that's formed between the ray and the actual normal line drawn there, which is drawn at 90 degrees to the surface, the normal line, and that carries through the surface there. On the other side you'll find the ray is bent or refracted, and that's called the refracted ray, and the angle of refraction there is the next one in there. So you can sort of see that. There's an example of that over here where it's actually a ray of light going to perspex, and you can see it's coming in there and it's actually bent down here, or bent up in this case. Bear in mind that whenever it enters a slower medium, it always bends towards the normal, and your angle of refraction here is going to be smaller in a slower medium than the angle of incidence. It goes the other way around when it comes out, by the way. If it was going out of a more dense medium that was slower, optically dense, then it would actually go to a faster medium and bend away from the normal. And you could reverse this here. So we're going to look at a law that actually sort of describes what the angle of incidence and the angle of refraction have as a relationship between the two. you can draw some analogies as to why it actually goes slower when it enters the new medium, and I've seen some different ones around the place. So one by here is the idea that when lights come down, it actually comes down as photons. And photons, when they hit the first layer of atoms there, get absorbed by the atom and then actually get re-released by the atom, and they get released after a certain time delay. So the fact there's a time delay there means that it actually travels slightly slower in this medium here than it travels in the above medium. So you could use that as one analogy. Photons get absorbed by a layer of atoms, then released after a short time delay. The next layer of atoms then absorb it and release it, and so on. And that could be one explanation as to why it travels slower in another medium like glass or water. And that slowing down obviously causes the wavefront to bend, as we've just sort of talked about. It goes from that angle and ends up going in closer together in this way. And that's a pretty poor diagram, but you get the idea. What we're interested in now then is what the relationship between I and R is. Now you could have plotted a diagram here of I versus R and try to find out if you get proportionality. Is I proportional to R? And the reality is it's not, and that's one of the practicals you've been doing, is to find out what is the relationship between I and R. So what we're going to do here is cheat and use the real one. So if you were to try plotting sine of I down the bottom here and sine of R on the side, you'll find you get a straight line because they are proportional to each other. I'll try and use a straight line here. It's a bit better than that. You'll get a straight line there through the origin. That's just missed. But if it's a straight line through the origin, you can actually say that the sine of I is proportional to the sine of R, and you can count the relationship. If you rearrange this, the typical sort of value we get in the textbooks in terms of Snell's law will say something like sine of I over the sine of R is equal to a constant value for a pair of media. So the constant eta, that's the Greek letter, might be from air to water, for example. So it goes from air into water. You might have a value of 1.33 for that, and that's the constant value for all rays of light going from air to water. And sine of I over sine of R is a constant. Now you can use that to work out a refracted angle if you know what the incident angle is, and vice versa. So they're the sort of questions we've been answering in class. So if you look at that there, we might do a couple. So if you had a problem here that was sort of like 30 degrees coming in, and we chose something like glass there maybe, we chose air, and you were told the refractive index for air to glass was 1.52, and they said this is the angle of incidence, what's the angle of refraction? You would try and find out the angle of refraction here by using Snell's law. So you're going to go sine of 30 degrees for sine of I over the unknown sine of R equals, and again the refractive index here is from air to glass is 1.52, and you can try and solve that. Okay, so when you come to do that, I'll be getting the sine of R at the top, so that'll come at the top here, and sine of 30 there, and we move the 1.52 down. So you're basically moving that one up there, dividing becomes times, times then becomes divide. So you're looking to solve for sine R there. So R will be sine to the -1, or shift sine, or inverse sine on your calculator, or second function sine. Sine 30 divided by 1.52, so it's 0.5 for the sine of 30 over 1.52. So you would do 0.5 over 1.52 and do the shift sine of that. So you end up with 19.2 degrees there, and you should check that because the angle of refraction here should be smaller because it's actually slowing down as it goes into glass. So at 30 becomes 19.2, that seems to make sense. So that's one way you should be aware of. So if you have a different question here, this time we'll try and find the angle of incidence, giving it an angle of refraction there of maybe 40 degrees. Okay, so in that case you're going to use the same formula, sine of I, we don't know this time, over sine of 40 equals the refractive index from air to glass. So we're looking at 1.52, and we're just trying to solve that this time. So to find sine I here, we're just going to go sine of I equals, this is divide by sine 40, so we times by sine 40, so 1.52 times by the sine of 40. You'll get that into your calculator and do the inverse sine of that answer again, and that will give it to you there. So you get 0.977, and if you do shift function of that here, you get 77.7 degrees. Hopefully what calculates in degrees. So there's another example there. So they're the two typical ways you can do it. Just bear in mind they might ask you questions where it comes from the ray of light going from glass back out into air or into a faster substance. So if you're going to do that sort of question, we're going to go reverse, and I'm just going to cheat again here and remove this one that's already there. So what if we decided to go the other way and the ray of light was coming out, and I told you that I this time was, say, 25 degrees, and I would say what's the angle of refraction as it comes out of the glass to there. So in that case there, one of the key things to be aware of is that the refractive index of going from glass to air is a reciprocal of from air to glass. So you need to do 1 over that. So in this case it'd be 1 over 1.52. And you can get a value there for that one. So if we now go back to our rule here, sine of I over sine of R equals that value there. So I might cheat there and put that in. So we're going to get 0.658 there. 0.658. So it's important that when you're going from glass to air, you actually do that reciprocal value there. We've got here sine of I is 25. So we've got the sine of 25 over the sine of R equals 0.658. And you're going to go through the same process of bringing the R up and that one down and doing the shift sine stuff again to work it out. But you should end up with an angle that's bigger than 25 because obviously it's going to a faster medium. It should have a larger angle there for refraction compared to the angle of incidence. So they're the sort of things you're doing. Now something else to bear in mind here, insert blank page, is that when you do come into a faster medium here, so if you go from air to say water, the ray of light is always going to bend away from this normal here, like that. At some stage you will find it'll get so bent that it comes out along the surface there with a refracted angle here of 90 degrees. Now when it does that, this angle in here is called the critical angle. Okay, and the critical angle there you can work out by substituting in to your formula sine of I over sine of 90 for the sine of R is equal to whatever your constant turns out to be. So you just have to remember that the actual value you're going to use is the reciprocal, don't forget, because we're going from water to air here. We need to do 1 over the refractive index of air to water, so 1 over 1.33. So that's about 0.75, or just a bit over 0.75 you'll find. So I'm just going to cheat there. So that's the problem you're going to solve. Sine of 90 is actually 1, so you're just going to do shift sine of roughly 0.75 there, and you'll find out what angle the critical angle is at. Anything bigger than that critical angle, of course, would do total internal reflection, is called, where the incoming angle is the same as a reflected angle. Normally you get some reflection, by the way, but this will be total internal reflection, and that's used going down optic fibres there then to send down laser beams, down telecommunications and so on. The laser beam that's sent down there, or down optic fibre lamps, just keeps on bouncing on the inside there and never comes out. So you will get the laser beam going down and keeps reflecting on the inside like that, transmitted down the other end at the speed of light. And that's the sort of use it's got. So that's called total internal reflection. Okay, I think they're the key parts we've been working on. I'll leave you to it. Thank you very much.